Okay, please, Daniel.
Yeah, thank you. Thank you for the welcome. So my name is Daniel Silver. I am a PhD candidate at Northeastern, and today I'm going to be talking about quantum machine learning on current quantum computers, specifically talking about some of the research my group has done into quantum machine learning. So here's just a sneak peek into some of the topics I'm going to be talking about today. So we're going to be covering image classification problems. We're going to be covering similarity detection, more of kind of unsupervised learning. And we're going to end the discussion of research in quantum image generation. So quantum computers, I'm sure many of you have heard, have extraordinary promise to sort of transform how we think about computing and a lot of the tasks we rely on computers for. But unfortunately, at the current time, they're very error prone, and they're actually defined by the current era of quantum computing, which we call the NISQ era, the noisy intermediate scale quantum era, where there's a lot of error throughout these machines. They're relatively small, so research has to sort of take this into account for current stage quantum computing. So here's an overview of how I'm going to be sort of structuring this discussion. So I'm going to start by an introduction into quantum computing. Many of you maybe have seen some of these concepts before, but I want to make sure we sort of establish a baseline for the rest of the discussion. Then I'm going to go into a little background onto machine learning. Then going to combine them into a discussion on an introduction to quantum machine learning, and finally end the discussion with the largest part of the presentation, which will be quantum machine learning research. So sort of to introduce quantum machine learning and quantum computing, we have to know about the qubit, which is the quantum analog of a bit. So where a classical bit can only exist in either one of two states, a 0 or a 1, a qubit actually can exist in a superposition of these two states, so that when we measure the output of the system, there is some probability we see one state and some probability we see another state, right? So it's not just a discrete number like 0 or 1. It's sort of a probabilistic measure between the states. So when we measure the quantum state, the qubit, we call it, we say that the position collapses and becomes sort of this discrete state. So while the quantum state is in computation before it's been measured, it's in this superposition where it's actually in this position of multiple states. But when it's measured, it becomes this sort of discrete state, which is what we observe. And it sort of collapses with this probability distribution where recall we have state one with alpha as a coefficient, and or sorry, state zero with alpha as a coefficient, and state one with beta as a coefficient. So if we take the magnitude squared of alpha, that's the probability we observe state zero in measurement. And likewise, if we take the magnitude of beta squared, that's the probability we will observe state one. And of course, these probabilities must sum to one. So the magnitude of alpha squared plus the magnitude of beta squared must equal one. So here are just some very simple example quantum states. So when alpha is 1 and beta is 0, we will only observe state 0 in this case, right? So we can see the probability of measuring state 0 is 1. Likewise, if alpha is 0 and beta is 1, we're going to measure state 1 100% of the time with a probability of 1. The more interesting cases are when it's not just 0 or 1. In this case, alpha and beta are both 1 over radical 2, as they're both equally as likely, and because we take the magnitude squared, we see each one has a probability of 0.5. So in order to manipulate these quantum systems, we use what are called quantum gates, which are unitary transformations that sort of transform one state to another. So in this case, we have state 0 and we have the identity matrix acting on it. And as you expect, it also resolves in the state 0. It doesn't change the state. Here we have the X gate, which is equivalent to a NOT gate classically. So when we take state 0 and we apply this NOT gate, we will always measure state 1. And here is the Hadamard gate, which takes state 0 and puts state 0 and 1 into an equal superposition where each state is equally as likely to occur. And this is the case where we might measure 0 50% of the time and state 1 50% of the time. So while it's interesting what we can do with 1 qubit, typically for these sort of more complicated tasks, we require multiple qubits for this higher level computation. And this is really where we start to see the potential advantages of using quantum computing. So, so we can actually take an n qubit system and show that it has 2 to the n states. So for example, here we have a 2 qubit system as 4 states. We have state 0, 0, 0, 1, 1, 0, and 1, 1, each with their own probabilities that are constrained by this same, the magnitudes squared must sum to 1. So 2 to 4, maybe we can start to see it, but say we have 5 qubits, and this will come up later, but a 5 qubit state can actually represent 32 different states. So we can start to see the sort of exponential representation we get from quantum computing. So these multiple qubit systems require multiple qubit gates to sort of interact with them. So take this example here. We have the CX gate, which is the controlled NOT gate. And what this does is it takes a 2 qubit system and takes the first qubit, and if it's turned on, so if the first qubit is a 1, the second qubit will flip its position from a 0 to a 1. And likewise, it'll flip from 1 to 0. So this is the C NOT gate. This is it represented as a 4x4 unitary matrix. And this gate creates what we call an entanglement, where once this gate has been applied to these operations, we can't fully describe the system in terms of only 1 qubit. Each qubit helps form this interdependent system where we can't completely just describe 1 qubit on its own and needs to be described relative to the other qubits in the system. Einstein called this spooky action at a distance. This quantum entanglement, where 1 qubit has this sort of immediate effect on another qubit. So by sort of transforming or measuring 1 qubit anywhere, these other qubits in this interdependent system will immediately sort of change based on whatever was applied to this 1 qubit. So to sort of recap why quantum computing is so powerful, we have these different properties. So superposition, again, allows qubits to exist in an infinite continuous state, which isn't just limited to 0 or 1 like a classical bit is. We have entanglement, which creates these rich connections between qubits to comprise a larger interdependent system. And we also are able to leverage these quantum gates to allow quantum computers to manipulate qubits using these unitary transformations. So now I'm going to go into a little bit of introduction into machine learning. So I'm sure as many of you are aware, machine learning sort of affects many aspects of our lives today. Here are just some basic examples. So chatbots like GPT models, these are all developed and based on machine learning principles. We also have image generation. You can see this sort of interesting novel image generated. This is all a result of machine learning. And then we even have applications into sort of the biomedical space with things like genome sequencing. So machine learning is sort of an umbrella term, but to try to define it, it really is just a broad term that focuses on teaching computers how to learn or interpret patterns in data, right? So this is sort of the general flow for a machine learning process. We usually start with a large sample of training data. We'll pass it through some sort of algorithm that it will learn to optimize. After this learning procedure, we get some sort of trained model afterwards, which we can then use to interpret some sort of results from, whether it's some model that's great at classifying if an image is a cat or an image is a dog, or it's a model that's great at generating text for a person to speak to. All of these are sort of like this inference stage that happens after the model is trained. So sort of the basics for all modern deep learning is based on what's called a neural network, which is a sort of function approximator, which is loosely based on how our brains function. So on the right here, we can see an image of what a neural network looks like. We have some sort of input data, and it creates some web of interaction through these hidden layers, which store some parameters that get learned over time to produce some sort of desired output. And again, this output could be anything from an image to a classification, is this a 0 or 1, to some likelihood of what a next word should be in a sequence. This output can be interpreted in many, many different ways. So neural networks are incredibly powerful, right? They can learn to approximate essentially any function arbitrarily well. And this is encapsulated in the universal approximation theorem, which states that a neural network can approximate any function arbitrarily well up to some specified, like loss or error epsilon, with only a two-layer neural network. Now, this two-layer neural network may have to be incredibly large, but it's possible given only a two-layer neural network to approximate really any function arbitrarily well. So this makes it very, very applicable to a variety of tasks. So the way neural networks learn is through a process called gradient descent, which essentially we take an input, pass it through the neural network, and we're going to get some sort of output. We'll call it y hat. We're going to take this output and compare it to some ideal output y, or some ideal objective, right? And then from here, we're going to apply what's called a loss function. So for example, L1 loss is we would basically compare y to y hat in terms of the difference in absolute values. That's the L1 loss function. The L2 is similar. It's the difference. However, we don't take the absolute value. We would square it and essentially say that that's our loss. And once we have this loss value, we use the gradient of the loss to sort of tweak the network based on how far the output y hat is from the ideal output y. And the idea is we're slowly descending this gradient curve until we approach some sort of local minima where we sort of optimize this objective function. In these functions, this is a very high dimensional space. There are lots and lots of local minima. It's very difficult, I guess, to find the optimal solution in general, but we typically rely on the fact that the approaching these local minima is sufficient to the task at hand. Even if we don't find the optimal solution, we find one that is practical and reasonable enough. So all that said, classical machine learning is incredibly powerful, but it does have its limitations, right? So like I briefly alluded to, these networks require a vast amount of training data, right? They require more and more training data, which is expensive, might be difficult to get, and might even be impossible for the required task. State-of-the-art models also require a large amount of training resources, which are just very computationally expensive, may not be feasible, maybe very environmentally detrimental, right? And we can sort of see that in this graph here, right? So these are sort of state-of-the-art models. So we can see like back in January of 2018, the state-of-the-art model was using 94 million parameters up until January of 2021, where it's 1.6 trillion parameters. And this only ends in 2021, but I'm sure this graph continues to soar. And not to say there isn't great research in machine learning that sort of makes these models more efficient, but a big reason for the sort of improvement we see in these in machine learning is just is having access to more and more computational resources, right? We really need these very large computers to run these larger and larger models. Another issue that a lot of these machine learning problems face is difficulty generalizing. as a lot of them can suffer from overfitting and sort of memorizing a certain set of data. So typically in machine learning, we have some training set of data and some testing set of data, which is sort of withheld from training. So the models might learn to memorize all the data in the training set. And then once we get over to testing data, it might be more difficult to sort of get the same accuracy or the same perform as well as we did in the training set once we go over to data it hasn't seen before. So that introduction out of the way, I'm going to go a little bit into quantum machine learning before we kind of start our discussion into the research today. So quantum machine learning has a lot of theoretical potential for speed ups over classical algorithms. One of them is an exponential speed up potential by leveraging, it's called the HHL subroutine, to solve linear systems in logarithmic time, although it has some caveats. But it should be noted that quantum machine learning hasn't fully been able to outperform classical counterparts today, although this is getting increasingly likely to change as quantum computers become more and more powerful. It seems every day now. So the sort of core to the research we do is focused on using what's called quantum variational circuits. And quantum variational circuits are really just, they're tunable circuits that can be optimized through training in a similar procedure to how neural networks can be optimized. There's a little difference though in the structure. Of course, these are on quantum circuits, so we have to acknowledge and work with the quantum properties we're sort of allowed through these variational circuits. But we also have a function of both fixed gates and tunable gates. Because in these quantum circuits, we need to enforce entanglements in some parts of the circuits. We have these fixed gates, which sort of can create entanglements and provide like a base structure for the network that don't change as we're training it. And also as we're performing an optimization, we of course need our tunable gates, which get optimized throughout training in this classical hybrid classical quantum sort of architecture where the gradients are computed classically, but are applied to a quantum variational circuit. So quantum variational circuits are very good for machine learning today. So they're just a really a natural choice for these noisy NISQ era machine learning tasks. So it's because, well, one, they can provide high accuracy and sort of high fidelity with very few parameters. They're much smaller than neural networks, but can still attain similar performance to significantly smaller neural networks. They can be optimized with the same procedures as neural networks. So a lot of research into classical machine learning can be applied here. For example, certain optimizers or certain loss functions don't need to be completely recreated. They can be applied to these quantum variational circuits, which sort of speeds up the research development process. And also they're small enough to fit on quantum computers today. So they're very scalable. We can make them sort of as small as we want or as large as we want. And the fact that we can make them small makes it so we can actually test on quantum computers today. But again, we do have these challenges. We have state preparation and measurement errors. So we have errors when we put data onto the quantum circuits and when we read the data off. We have errors throughout the gate operations. And then we also have phase and dampening errors. So all of these together form sort of, they sort of cascade among one another and make the overall fidelity of the circuit poorer than it could be. Right. So by improving just one of these, we really improve the fidelity. But we have to sort of keep all of these in mind for our quantum machine learning tasks. They have to be relatively robust to noise. So now I'm going to talk about the quantum machine learning research, and I'm going to start by talking about quantum classification. So one of our works, which we had published in date of 2022 called Optic, is a binary classifier. So the idea is to basically program a quantum classifier by training in an ideal classical simulation of quantum computing, right? We train in this sort of noiseless model. The next stage is to really run multiple models on multiple computers, just with more and more samples of data, which we then optimize through using dual annealing. Then we can run the request on real quantum computers and classify the final model. And we find that the variants provide a significant boost in the classification accuracy on real NISQ era quantum machines. And then we find it also becomes increasingly effective with the inclusion of more machines and actually outperforms the best combination of a smaller set of machines. And while this is well and interesting, and binary classification certainly comes up, many real world tasks require classifying more than just two classes. So then we move over to how to perform multi-class classification on quantum machines. So prior to our work here, the sort of state of the art had been to use repeated cases of what's called one versus one classifiers. So the way this works is it's just a series of many small binary classifiers where there's one for each combination of classes. So in the case of, let's say we're trying to classify between cases 0, 1, and 2, we would have a 0 versus 1 classifier, a 1 versus 2, and a 0 versus 2 classifier. So as you can imagine, every time we add a class, we need a linear number of classifiers added as well. So this, in fact, scales quadratically, which we can see here for the models needed for this 1 versus 1 classifier. And it becomes significantly worse, right, as we increase the number of classes with the scaling. Likewise, we actually find that the accuracy scales sort of inversely. The accuracy gets significantly worse as we add more of these 1 versus 1 models, and we find a large drop off as we increase the number of classes, which we can see here on the right. So it does have these sort of scaling shortcomings, right? We do have limited resources on these NISQ era machines, and also accuracy shortcomings, right? It's not very robust because if one model is off in these, maybe 25 some odd models, we get a significant degradation in accuracy. So it's many points of failure here. So our solution was to introduce an ensemble-based approach we called QuILT. Here's just a general overview. I'm going to go into each of the components separately. So we sort of take many classifiers, which we perform inference on. We find a way to aggregate the different members of the ensemble, and each member is really just its own classifier. We then look at where it's least confident and sort of adjust our guess based on the confidence of the model. So again, an ensemble is really just a group of individual classifiers. And it sort of comes from the idea of there's this old jury theorem that states as we increase numbers of members in a jury, if each one thinks sort of uniquely and is over 50% accurate, as we sort of approach like an infinitely large jury sample, we will approach a correct guess on a verdict, right? So that sort of idea is what kind of creates the intuition for an ensemble. If each member thinks uniquely and is accurate, we can actually aggregate them together to create like a more powerful device than what each one could do individually. So in order to aggregate the ensemble, we get a weight which is for each member, which is applied to the aggregation. We then take the sign function, which is used to transform the poly-Z measurement to a distinct class output. The poly-Z measurement is just a way of measuring a qubit that sort of that gives us an output between -1 and 1, right? So we can basically say if the output is negative, it means the model has guessed class 1, and if the output is positive, it's really guessed class 2. So the question is how to actually weigh these ensemble members. Traditionally, there's different approaches. The simplest idea would be each ensemble member is sort of weighted equally. And this would be what's called a majority rules approach, where whatever most members agree on is what the output is, right? But we actually found that there's a better way to sort of aggregate it in this sense, and that's to look at the relative accuracy of each model. So the models that do better in this case are weighted slightly higher. And we use a simple like training accuracy. So depending on how well the model performs in training is sort of what we use for evaluation for weighting the members at the end for classification. So the model construction is to take this core classifier, which is capable on its own of performing a multi-class classification. We take these diverse variants, or what's called different onsets of core classifiers. We essentially change the architecture of each of these quantum circuits slightly to try to enforce that they think differently. They have like a different way of evaluating the same piece of data to enforce that diversity in the ensemble members. And then we actually use what's called a one versus all classifier for error correcting. And the one versus all classifier is really, it's similar to this one versus one we had mentioned before, but instead of being quadratic, it's linear. And we just apply, for example, if we have 8 classes, it would be looking at, the one would be maybe looking at 0, and then it would be versus 1 through 8 or 1 through 7. So it's a binary classification between one class and every other class. We find that's actually very useful for the error correcting procedure. This is something you might be used to seeing if you have seen a lot of machine learning work before, but this is sort of the methodology for how we process this data and run our training procedure. So we take this full data set of images, and we split 80% of it for training, and we withhold 20% for testing, so the model doesn't necessarily overfit on the training data, and we can actually see how well it does on novel data. Because again, we are limited by the size of the quantum computers, we're using 5-qubit computers, so we can actually reduce the data through principal component analysis to an input of size 32. And because with 5 qubits, we have 2 to the 5th, I guess, amount of states we can put on our system. We can put all 32 features of the principal components onto a single 5-qubit circuit. We use L2 loss, which remember is the squared loss for output. We use Atom Optimizer as our optimization function. We use a batch size of 40 with resampling, and we train for 100 epochs or training iterations. So here's how accuracy sort of scales by the ensemble size. So we find that adding more ensemble members typically does increase the training accuracy, but this is especially the case when we have different variants of the circuit architecture. So this is using MNIST-4, which is just 4 classes of the MNIST data set without any error correcting. And this, for our future plots, will just be called ensemble. So here's how the technique QuILT performs over the MNIST data set for a different number of classes. So we find, especially as we get more and more classes, especially as we're going to 4 and really as we go to 8, we significantly outperform the other models. Remember, the 1 versus 1 is just the previous case where we have a quadratic number of models. And ensemble is sort of without the improvements that we mentioned in QuILT. It's sort of a basic quantum ensemble approach. So we find sort of in all of these cases, the scaling is just much better, and the accuracy is much better using QuILT. And then we decide to look, instead of just looking at the MNIST data set, we also wanted to look at other data sets as well. So we also look at Fashion MNIST, which is a slightly more difficult data set than MNIST. Instead of looking at image digits or digits of images, or images of digits, it's looking at images of sort of like clothing. So there's shoes, handbags, t-shirts, things like that. But it's still these sort of grayscale images of 28 by 28 pixels. And then we also take a look at CFAR, which is the most difficult data set of the bunch here, which are images in color that I believe have like birds, airplanes. It's just more complicated. than MNIST and fashion MNIST. So we can see that here. The accuracy for CFAR is the lowest across the board. It's the most difficult data set. But we still find that in all of these cases, Quilt is able to outscale and outperform the other models, both using 4 classes and on the 8-class case. We see in the 8-class case, certainly there is some degradation in image quality, but the scope of the problem increases. So this is what we expect to see. We then want to test the model on real quantum computers. So in this case, we take a few of IBM's computers, IBM Lima and IBM Manila, and we look at the accuracy of our model, the 1-versus-1 model, and the ensemble model. And in the 4-class case, we find that Quilt still significantly outperforms the other classes. And what you might see here for half noise is an interpolation between ideal simulation accuracy or ideal simulation noise, which is 0, and what we actually see on the quantum machines, the actual noise rate. So we sort of perform an interpolation and apply that noise rate, and we see, with this reduction in noise, a significant improvement in accuracy. And as the noise increases, right, with what we can see on the right here, the accuracy increases significantly as these errors compound less and less. You might notice on the graph on the right that the 1-versus-1 is missing for Lima and Manila. And this is really just a resource constraint. Remember, the 1-versus-1 requires a quadratic number of models. So for 8 classes, it was impractical to really run these rigorously on real quantum computers. So that's why we only have the half noise there. And as we approach this sort of simulation accuracy, we also know that Quilt will continue to outperform the other models, as we saw in the ideal simulation. So next, I'm going to go into quantum similarity detection, sort of an unsupervised learning problem. So similarity detection is useful because often labeled data isn't made readily available in the real world. What it is it really works to find patterns in unlabeled data. An example of this might be a doctor trying to diagnose a complex disease based on medical images without a sort of quantifiable label. This is sort of like a similarity detection problem. Given these 3 images, which one is most likely to have this sort of disease or something like this? It's also really useful for recommendation engines, such as in music recommendations. So this could be, I'm sure many of you have used music streaming services, and you might see that certain music may be catered to you. And one of the ways this could work is through looking at what other users listen to, instead of having a person labeled as some sort of, this is a country music listener, this is whatever, a pop music listener. You might have a more nuanced music taste, which can't be labeled. And instead, the best way to recommend you a song is to recommend you a song that other similar people have listened to. So that's where we sort of get into triplet networks. So at this point, I'm only talking about a classical triplet network. So what triplet networks are great at is they can create an embedding based on some ground truth similarity, which doesn't necessarily need to be set as a label. So we take triplets of data, three pieces of data, an anchor, a positive, and a negative image, where there is some ground truth similarity where the anchor image is closer to the positive than the anchor is to the negative. And it could be based on any rule. Going back to the music example, these 3 could be two songs that one person listens to, anchor and positive, and the negative could be a song they don't listen to. And what we get is this sort of high dimensional embedding where we get similar pieces of data mapped close together based on whatever rule we want to define. So that's where we that sort of sets the basis for quantum image similarity. So our work, SLIC, which was published in AAAI in 2023, focuses on this sort of quantum image similarity detection problem. So the idea is to entangle images and design a network around pairs to leverage the scaling properties of quantum computers. And remember, because the properties of encoding data into quantum computers, we can encode 2 to the n states. We only need one more qubit to encode double the amount of input data. And the idea is to, we also work on interweaving pixels one at a time to create strong entanglements. So taking an input data set, we convert it into anchor positive and anchor negative pairs. In the classical case, we have anchor positive and negative separately. In this case, we can actually entangle it. So we have less runs of the data, right? So we have anchor positive entangled and anchor negative entangled. We train the network using the data set and use it to sort of infer a class or a cluster, basically how close new data is to the existing map data. But one issue that sort of arises from this approach of having anchor positive and anchor negative, while we do get a reduction in runs, we do have the issue where we have 2 different mappings for the same image, right? The anchor image, which is in both the positive and the negative, could be mapped to a different place, which we don't want, right? We want the same image to be mapped regardless of sort of what the other entangled image is. So with projection variance, this sort of distance between the anchor mapping, the image will end up, the anchor image will end up being mapped separately based on what the other image is. So the solution is to add a constraint in the form of a loss function to sort of mitigate this projection variance. So our overall objective function now has to take into account this projection variance as well. So we have sort of 2 terms in our loss function, right? We have the original objective, which is sort of how close the anchor and positive are together, minus how far the anchor and the negative are together. Because remember, we want the positive and the anchor images to be closely mapped, and we want the anchor and negative images to be mapped far away. So that's one objective. The other is this performance or this projection variance mitigation. So we sort of have to balance this alpha and beta based on how much we want to focus purely on the objective versus on the projection variance. So taking this model, we sort of pose an unsupervised problem for the model to solve. We take a bunch of images from the Flickr landscape dataset, and we say how similar are the images based on their color frequencies. So if an image has a certain amount of red hues versus blue hues, we use this to sort of create these triplets without any specific label, but just by saying that the images with similar color frequencies randomly will be built into these triplets. And we want our model to be able to learn an embedding that sort of models this these triplets of data. So we find that up top we use sort of a baseline, which is just sort of a vanilla triplet network on quantum computers, and on the bottom we have our slick model, and we find that we perform significantly better on identifying similar data based on this this sort of similarity detection. And we can see this maybe a little more clear here. So we use the Spearman coefficient to compute to compare the base triplet design to the proposed method. And we can see at every percentile in the Spearman coefficient, there is an increase in the sort of detection potential of SLIC versus this baseline vanilla approach, such to the point that SLIC identifies similarity between images 31% better than the baseline method on unsupervised data. And what we can see in this picture here is we have our anchor image, and then we have what the baseline guesses as the closest image, and what SLIC guesses as the closest image. So we can see here up top, this sort of rock in the beach. SLIC identifies an image that is more similar than what the baseline can identify. So even though the SLIC image isn't a rock in the beach, it looks like a sort of a mountain by the sky. It picks an image with much more similar color frequency, which is what it's trained on. So it does a much better job over the baseline. Likewise, we have another image, looks like sort of a blue mountain, and the baseline gives, as its most likely similar image, it gives an image that is not really close, whereas slick gives a much more similar image to the anchor. We also, while this approach is mostly for unsupervised data, we also just test on labeled data sets as sort of an experiment to see how well this could work at something like classification, even though it's not really what it's built for. So we can actually create triplets by looking at data in the same class and data in different classes. So the triplet could be composed of three points, the anchor, the positive, and the negative, where anchor and positive are both from class 1, and the negative could be something like from class 7. So what happens is after this, after these triplets are constructed and the model is learned, we just sort of have an embedding, right? So in order to go from an embedding space to a classification, we use just a simple Gaussian mixture model to cluster the data. And of course, we don't know which clusters correspond to which labels, so we have to consider every combination for it to basically see how well this would perform at accuracy, right? By creating these different clusters. So we can see it actually performs relatively well for accuracy calculations, despite not being a classifier. So the next research topic I wanted to go into is quantum image generation. It's still unsupervised, like the similarity detection was, but of course this is focused less on, I guess, analysis, more on generation. So, and specifically, we're going to be talking about image generation using GANs, which are generative adversarial networks. A GAN is really just two neural networks, a generator and a discriminator, which are trained simultaneously in a competitive process, where the generator takes in random noise to generate fake data samples, while the discriminator's goal is to distinguish the real data from the fake data. So on any given run, a generator takes in random noise, creates some sort of image. At first, it's going to look like noise. The discriminator takes in real images some of the time, and the generated images some of the time. And its goal is to try to differentiate the two. So over time, as the discriminator gets better as a classifier, the generator is going to get better at generating fake images, and they sort of create this process until they reach some sort of equilibrium where neither network is able to improve further. So one work that is going to be published at ICCV in 2023 in October is our work called Mosaic, which is a quantum image generator, right? It's a GAN. So on the left, again, we have this classical GAN approach. On the right is just a simple is the Mosaic approach. So because we're using a quantum system, things change. So we are using a quantum circuit as our generator and a classical network as our discriminator. So we still take the random noise into the quantum generator to pass into the classical discriminator. And we take the images, apply some transformation, and also pass to the discriminator. And then the discriminator will tell us, is this a real image or is this a generated image? So building a quantum GAN. So the idea is to leverage a hybrid configuration with this quantum generator and a classical discriminator, again, training simultaneously in this adversarial game. We use what's called patching for the generator, where multiple sub-generators work together to each generate like part of the features, part of the image. So each one sort of gets appended together to create what the full generator's output would be. And in fact, one of the techniques we propose here is training the generator to learn principal components instead of learning the pixel values directly, just to make this sort of a more scalable design. So the generator will learn to create features that then can be inversed from principal components back to the original data set. One quality about principal components is that each principal component in a PCA decomposition is not distributed equally. So the first feature will always contain the most amount of information about the data set, with each subsequent feature preserving less and less information, which is called explained variance here. So if we only assigned some sub-generators to learn the important features, we're not really making good use of all the generators to learn what's relevant here. So one way to think about this is if we have 10 generators and one of them is the only one responsible for uh, learning the important data, all the attention and the gradients will be focused on that one generator, and we won't make adequate usage of all of our quantum resources. So we redistribute the PCA features so that we try to sort of equally disperse the amount of information that's relevant for the uh, for the PCA between all of the different quantum generators. We find overall improvement in image quality across the board. So we use what's called the FID score, which is a measure, it's similar to inception score. It's a measure of sort of image quality on images generated through neural networks. And we find that without this PCA redistribution, we have worse image quality, which you can see here. The distribution is shifted to the right. An FID score we want lower because the lower FID score, the better the image quality is. So we find across the board that this distribution creates much higher image quality. We also introduce what's called adaptive training noise. So remember, GANs take input noise and transform it into images. We find though that using a large range of noise, right, leads to a lower image quality because the training procedure becomes more difficult. So the noise that goes into the model is sort of is randomly sampled, and in this case, just for illustration, if our noise can range anywhere from 0 to 1, we might find that that leads to low image quality. It's a more difficult problem to transform all of it. So a low noise range, 0 to 0.5 or something, might increase the image quality, but unfortunately has the effect of making all images look the same, right? So we have to find that like ideal trade-off between low image with a low image variety and low image quality. We want high quality images of different variety to create a good generator. So our solution is to actually adapt the training noise based on the balance between the generator and discriminator throughout training. So what we basically do is we look at the ratio of the generator and discriminator loss, how well is the discriminator learning compared to the generator. And based on that, we allow the generator to explore a more complex space. So as the generator gets better relative to the discriminator, we also throw in, we also let the generator explore a more complicated space of generating different variety of images. And when it gets worse, we let the generator just focus on creating high fidelity images. And this sort of, we create a mapping between pi over 8 and 3 pi over 4, which is sort of our bounds for the noise, which we found through experimentation to be the best. The tan function here basically maps from -1 to 1, whatever range this might be, and then we map again with ReLU from 0 to 1, so the whole thing is bounded from pi over 8 to 3 pi over 4. We find that adding this adaptive training noise produces a higher variety in images compared to the static image ranges. And we find that it also helps mitigate mode collapse. Because one issue is, even though we might have high image quality, if all images look the same, our generator isn't performing well, right? We say that the variation is also very important to the image generation process. So to put it all together, the way this works is in training, we take our random noise, we apply PCA and put it on the quantum generators. We then concatenate the outputs of the generators and reorder based on the PCA features. We pass that to the classical discriminator network, where we get the generator loss and discriminator loss, which then calculates the new noise range, which then goes in to create the new random noise that goes into the next iteration of quantum generators. The inference procedure is simpler. It doesn't need the classical discriminator at all. We take the random noise, pass it through the generators, concatenate reorder, apply the PCA inverse transform procedure, and get a generated output image. So here's some of the results. So employing the aforementioned techniques delivers high quality image generation compared to the previous state of the art, which is QG patch. And we can see here on the left, looking at digits 0, 5, and 9, overall, Mosaic produces images that look much more like the input data set than QG patch does. The images are far more human recognizable as well. And then the case is made especially more true when we look at the fashion MNIST data of boots, t-shirts, and trousers. The boots and the t-shirts and the trousers all look more human recognizable. And these are all, this is all from a simulated quantum circuit. So looking at all the classes in general, we found that Mosaic outperformed QG patch on every MNIST digit and also on every fashion MNIST digit, higher image quality in all 20 cases. We then applied this on a real quantum computer with real noise, which is IBM's Jakarta. And we found that on the images we tested, there was much higher image quality and much better preservation of the image quality with Mosaic versus QG patch. So in all cases, Mosaic may look may look slightly worse, right? But this is because noise is introduced to the system. But it still produces recognizable images in every case on the real quantum computer, whereas the QG patch really suffers from the introduction of noise. It's less robust to the noise model and produces less recognizable images across the board. Thanks everyone for coming and listening. Here's an online textbook I recommend. Some Penny Lane tutorials, which is sort of the framework we use for quantum machine learning, which again has fantastic tutorials. There's an IBM lecture series, and here's my email if anyone wants to reach out with any questions. Thank you.